welcome to the afternoon session. Thanks for being on time after lunch. My name is Kasimir and this research has been conducted together with colleagues Jannic Höper and Sebastian Theißen from Bergische Universität Wuppertal in Germany and Jakub Veselka from Czech Technical University in Prague. And so basically, as most of you might not be familiar with life cycle assessments, I'm gonna focus on that in the beginning, and then we had an extensive state-of-the-art part in our paper and came up with a proposed methodology we would like to discuss and end with conclusion and outlook. So the background of our work is that currently, I already presented in the thesis in 3 presentation right before, the global CO2 emissions in the building sectors are responsible for 40% of the global emissions, and we can distribute this 40% amongst residential buildings, which is 43%, and 57%, which are non-residential buildings. And additionally to that, 11% from the worldwide emissions are directly connected to material manufacturing. And the next fact is that usually when we're looking at the masses of buildings, 1 to 4% are only relevant or relied on technical building services. Technical building services include electrical engineering as well as HVAC, so different disciplines. But usually when we're talking about HVAC, so heating, ventilating, air conditioning, they're responsible for 20 to 30% of the greenhouse gas emissions, so CO2 emissions, over the whole life cycle, when we're talking especially about embodied emissions. And one extensive study was done by André, who investigated in very detailed these embodied emissions and also operational emissions. On the left side, you can see the greenhouse gas emissions of a so-called electronics-based system building, where you can see, on the bottom part, the blue phases A1 to A3, B4 is exchange rate, and C2, C4 are the embodied emissions phases, and B6 is the operational phase. So you can see here the impact of the embodied emissions on the whole life cycle of this building is much bigger than the operational phase. On the right side, you can see of the embodied emissions how the distribution is connected. So you have in dark blue the structural and architectural components, and then in more detailed the HVAC and the electronics of the building. So you can see here, usually I'm showing this because usually we don't consider in embodied emissions calculations in life cycle assessments, usually we don't consider embodied emissions of HVAC or electronics in detail, but usually you just put a benchmark of 20% on it. But when we're talking about optimizing embodied emissions, we are not considering today technical building services. So generally, to make this workflow automated and reasonable, because there are some studies, but it's very takes a lot of time, is a very time-intensive calculation. That's why BIM, of course, as a methodology, gives a big potential to automate this process. There are 5 different strategies of integrating LCA and BIM, but the authors of these integration strategies mainly also focus on the architecture and structural part, not so much on the HVAC part, because usually when you can see here as an initial input is the BIM software, but you don't have, or in this categorization, you don't have different disciplines, but only, again, architecture and structural inputs. So what we wanted to do in our literature review, we first checked all the relevant, or the 4 relevant topics: BIM, LCA, so a life cycle assessment, HVAC as the main contributor to technical building services, and early design phases. And we had a deeper look what literature is out there in the overlapping topics, so LCA and BIM and so far. But what we're actually interested is the middle of this graph, LCA for HVAC or technical building services, and early design phases and BIM. And for that, we had a deeper look on literature analysis where we had these different classifications. So when we're talking about, when I go back, LCA and HVAC in early design phases and BIM, there is not such a methodology yet. So what we were looking at, what similar methodology are out there. So that was the core part of our classification, and we came up with basically these around 10, 12 publications, which mainly lead to two different trends in this field. So one is including technical building services in early design phases, but not considering a BIM integration. And the other one is including lifecycle assessment of technical building services in detailed phases based on a BIM integration. So we have a BIM model of an HVAC or electronics domain, and then we can, in the detailed phase, calculate a holistic LCA, but in a detailed phase, we can't optimize the decisions. So what we're basically proposing, a mixed approach. So I showed this slide also already earlier. We have in the early design phases a lot of unknowns, and when we're looking on buildings, we know some elements, structural elements, architectural elements, but on the left side, for example, HVAC elements are not designed because usually the HVAC designer is modeling or designing after the architecture is more or less already decided. And on the right side, you can see in a detailed phase, we know already all the materials and elements. So lifecycle assessment mainly bases on material specific data sets. So we have these two trends of in early design. We usually do top down. So we have benchmarks generally. I already mentioned, usually you just calculate 20% on top. But this is not precise, and this doesn't help for optimizing. On the right side, we have the bottom up, so we know already all materials. We can calculate the LCA, but we can't optimize it as it's in a very detailed design stage. So what we want to do is taking that knowledge from the detailed design phase and predicting the missing elements. So from the early design phases, we want to base the proposed methodology on low LOD models, so a low level of development. And from the detailed phase, we want to take the knowledge about how certain elements are influencing the lifecycle assessment and which different design options we have and bring it to the early design phases. So finally, our methodology we propose consists of a knowledge database, which consists of different design variants and different LCA profiles, which are fed from LCA databases. So that's the core. But then we say we base our methodology on an architectural BIM model. So we just have, as usual, this as a first low LOD model. Then we can pre-assess different variants. I'm going to show later how this could work. Then we have to consider different norms, how you, in a standardized way, pre-dimension different domains such as heating or ventilation or cooling. And in the next step, we can calculate the embodied emissions of different variants. Once we have the variants calculated, we can select it and finally give this information of the selected variant back to the HVAC or electronics domain, and they are modeling then their detailed BIM model and can do a clash detection with the architectural model. But we have this LCA calculation brought it to an earlier phase where this, except of just only costs, can also include embodied emissions. And before the model of the detailed TBS is set up, we have already first assumptions or first design variants we can consider. About the knowledge database, as we're mainly based in Germany, but also the ÖkoBauDat is the German LCA database. It's one of the most extensive LCA database we have so far in the world, specifically for construction industry. And on the right side, which is mainly focusing these LCA profiles, but also the design variants, there's a research quite already old from Weisenberger, who came up with a simplified approach on how to get these LCA profiles assumed and also considering design variants. And when we're talking, we had also another paper on this variant filtering. We have a lot of constraints when we're talking, so that's from a different publication which was presented beginning of this month at a different conference. We have different constraints when we're talking about different domains. So here we showed on the left side structural, and in the middle building envelope constraints, and on the right side, for example, only the heating system. We have, depending on different decisions in the architectural and the structural model, only different options we can filter in the, for example, in this example, heating system. So this needs to be filtered, which options can be selected. And as a case study, we, together with a student, implemented it in this educational building. So that's the input, the architectural BIM model. We prepared the database for the ventilation case with this MH software, which is basically integrating the standards and norms on how to dimension ventilation systems. We could arrange with some manual inputs the first preliminary ventilation model, but just very sketchy, so it's just a line model, so not a volumetric model. Then we could select different design variants, we could look into different design variants, then select one of the variants, and finally give this back to the domain expert in ventilation, which would then model the detailed ventilation model, and then do a clash detection. In the end, I want to conclude and state again that the literature analysis shows it's a complex topic because there's so many influences, and there's not in this specific combination any literature yet. It has limitations. It's a new methodology needed, which we try to propose with our mixed approach from taking domain knowledge in early design phases and with assumptions predict certain variants. BIM enables an automated and integrated approach, as we could see, also in early design phases. Yet a little data set, and that was the biggest problem on HVAC and electronics, is in these databases. So also these benchmarks are not available, so these have to still be contributed. That's one of the main limitations so far. And the next steps would be then really to further prototypically implement, as we showed with the ventilation, but on different domains, and establish these benchmarks and data sets to get a fully proof of concept. That was my presentation. I thank you very much for your attention, and I'm open for questions now.